Have a good day, everyone. This is the group 2, and now we're going to tackle about the translation. So translation is a term used in geometry to describe a function that moves an object a certain distance. So let's start and enjoy.
Translation is a geometric transformation that moves every point of a figure, shape, and space by the same distance in a given direction. It can also be interpreted as the addition of constant vectors in every point, or as a shifting of the origin of coordinate systems. What is a constant vector? A constant vector is the one that does not change with time or any other variable. Translation is also a simple way to describe the product of two reflections with parallel lines. Here are real-life examples of translations. Aircraft moving across the sky, throwing a shot put, elevators, moving cars, and many more. If M and N are parallel lines, we may choose P arbitrary to M and choose Q to be the foot of perpendicular P to N. If N is a unit normal vector to M, we get x plus 2 times the difference of P and Q, where P and Q is perpendicular to M.
Okay, have a good day, everyone. I am Naomi Cedeno, and now we're going to talk about the definition of translation. Okay, let's read it first. The definition of translation. Let L be any line, and let M and N be perpendicular to L. So the transformation omega sub M and omega sub N is called a translation along L. So if M is not equal to N, the translation is said to be non-trivial. Okay, so when we say non-trivial or not equal to 0. Yes, okay, translation. So translation are sliding shapes. Remember that the object or shape is not altered in any other way. It is not rotated, reflected, or resized. So in a translation, every point of the object must be moved in the same direction and for the same distance. So when you are performing a translation, the initial object is called the pre-image, and the object after the translation is called the image. So in the picture, the rust colored item is the pre-image, and the blue item is the image. So we know this because the arrow tells us the direction in which the image was moved. So for other images, you might be told which image is the pre-image, or you might be asked to find either the pre-image from the image or the vice versa. So next, how to perform translations. So when working with translation problems, the information may be presented in different ways. So you may be given a figure drawn in the coordinate plane like this. So in the left side, it is the image on coordinate plane. So, okay, then you will be asked to translate the figure. You will be given a distance and direction for the transformation. So, for example, translate the figure down 7. The way to do this is to take each vertex point individually and count down 7. So, the point at 1 and 5 will move to 1, 2, and negative 2. So notice we did not move the vertex along the x-axis or horizontal direction. The instructions ask to move it down only. So along the y-axis, move the other 3 vertices in the same manner. So the point at 3 and 5 moves to 3 and negative 2. 1 and 3 moves to 1 and negative 4. And 3 and 3 moves to 3 and negative 4. So this is the image translated to down 7. So that's all. Thank you for listening and God bless.
Okay, let's move on to the Theorem 24. The topic will be translation, and we will discuss the definition and proof describing the product of two reflections. So, on the Theorem 24, let T be a non-trivial translation along L. The L has a direction vector such that Tx is equals to x plus b, for all x is the element of Euclidean plane. So the non-trivial translations along line x is equal to any line along x plus the direction vector. For instance, any point of the line is element of the Euclidean plane. So meaning in Theorem 24, if V is a non-zero vector and L is the any line towards the direction of vector V, then the transformation along the line is a translation. So we have our proof. Let N be a unit direction vector for L. Let P be an arbitrary point for Euclidean plane. Let alpha and beta be lines perpendicular to L. And let A and B be the unique numbers such that arbitrary point P and the sum of the unit direction vector for unique numbers A is an element of alpha, and arbitrary point P and the sum of unit direction vector to unique numbers B is an element of beta. Okay, in this figure, it is said that N is a unit direction vector for L. So first thing we're gonna do, we will going to make a line for L, and we will going to put N here to represent the unit direction, and P be an arbitrary point. When we say arbitrary point, it is undetermined or not assigned a specific value. So we have to put P here. And let alpha and beta be perpendicular to L. When we say perpendicular, it is a line that intersect to form an angle. So this is the alpha and this is the beta. And let A and B be a unique numbers. So our unique numbers here is represented by the x, x prime, and the x double prime. Therefore, the arbitrary point P and the sum of the unit direction for unique numbers A is an element of alpha, an arbitrary point, and the sum of the unit direction to unique numbers B is an element of beta. So now the formula of Theorem 24 becomes omega subscript alpha times omega subscript beta times any point x in the line is equal to 2 times quantity P, which is the arbitrary point in Euclidean plane, plus the product of a unique number A and a unit direction vector N, minus P, which is the arbitrary point in Euclidean plane, minus the product of a unique vector B and a unit direction vector N. The result is equal to x plus 2 times quantity A minus B times the unit direction vector N.
Definition: the set of all lines perpendicular to a given line L in Euclidean plane respectively is called a pencil of parallels. The line L is a common perpendicular for the pencil. See figure 1.24. So if we can see a set of all lines that is perpendicular to the given line L, which is it is in Euclidean plane respectively, then we call it as pencil of parallels. Then the line L is a common perpendicular for the pencil. It is a given perpendicular for the pencil.
So for your information, a pencil of parallel lines is a maximal set of mutually parallel lines, or equivalently, a set consisting of line together with all the lines parallel to it. So if we define two lines in plane to be parallel, if either they are equal or they do not meet, then parallelism is an equivalence relation on the set of lines in an affine plane. The equivalence classes of this equivalence relation are the pencils of parallel lines. Next is, here we go, the figure 1.24. It shows a pencil of parallels with common perpendicular L. So as you can see in the figure, this line is what the given line L. Then the set of lines, which is this one, 2, 3, 4. The set of lines which is perpendicular to the given line L is what makes this figure a pencil of parallels with common perpendicular L. So if we can see a set of all lines that is perpendicular to our perpendicular to our given line L, then we call it as a pencil of parallels. Next is, we note that taking any line M and Euclidean plane respectively together with all lines parallel to M would be an equivalent construction. So it's either in line M, but then it is in an Euclidean plane respectively together with all lines parallel to line M, then it would be an equivalent, or it has equivalent construction. So far, we have discovered that the product of two reflections in line of a pencil parallel is a translation along the common perpendicular L. We now investigate further the algebraic structures of the set of isometries formed by reflection of such a family. So now we know and we discover that the product of two reflections in line of a pencil of parallels along the common perpendicular line L is a translation. So we need to take note that the product of two reflection in lines of pencil parallels with a common perpendicular L is a translation. We begin with the translation. We denote the set of all translation along L by trans L. So now, if we are going to denote, or we are going to write the set of all translation along L, then we can denote or write it as this one, by trans L. So take note, if we're going to write the set of all translation along L, then we can write it as trans L. So that ends my discussion.